Okay. Howdy, everyone. Welcome back. Second class of 322 for this semester. You might have noticed I just sent you like 20 minutes ago the PDF of today's slides. I had some technical issue with that too, with the listserv, but hopefully it's resolved. And as I mentioned on Wednesday, I will keep doing that for the remainder of the class. Okay, I will send you that in advance. Then we do the class depending on what I'm able to cover, or if there are any questions, anything that I need to update, I will do that, and I will post them on Canvas right after class. Okay. Other than that, any question before I begin and continue with the introduction on the engineering economics? No one? All right. So just to remind you what we're doing, I use the first class to give you the introduction, the basics. We define, you remember, the cash flows, we define the end of the period convention and the associated interest or interest rate. Okay, and we are going to be using those concepts for the next month or so. At the end of the first class, I also introduced the concept of economic equivalences. Okay, remember that, and we're going to be using that today and on Monday and beyond. To refresh your memory, what we mean about economic equivalences is this is the last slide of last time. Okay, it's not new. We have defined the cash flow. So depending on when a given transaction is placed throughout time, you can find an equivalent amount anywhere else in the cash flow, provided that you have the time difference, how many periods is before or after, and associated interest that is governing that cash. Okay. With that in mind, with a single transaction, you are able to find any future equivalent amount which is equal to the given, let's call it present amount, even though I want to say now because it will be deceiving at some point. The symbol are F and P because they stand for future and present. Nevertheless, this is just a symbol, okay? It just represents an amount that can be anywhere in time, okay? P doesn't necessarily has to be now. It can be anywhere in time, also in the future as well, okay? Keep that in mind. But for this simple example, we started with the present. So present is obviously time zero, okay, or period zero. So with that said again, any future amount or even any past amount, if you want, can be equivalently calculated using this simple conversion formula, okay, which gives you a formula including the interest rate associated within those two periods and how many periods in between the two transactions we have, which is represented by that. If you invert this formula, you can get any, let's call it present amount, calculated in function of a given future amount. And as you can see, there is a minus here, so it's just the inverse of that formula. Okay, it's the same exact mathematical equivalence, it's just solved for one or the other. Okay, should be pretty straightforward, and we'll build on it. With this in mind, let me get into a little bit more notation that will also going to help us use the tables which are on the back of the book. I didn't mention that yet, but I will today. I will show you also, I have the book today, so I will show you the back of the book tables that you will be welcome to use. And sometimes they're really useful, as we will see later, because the calculation becomes a little bit cumbersome in some of the equivalents we're going to be doing. So rather than plugging in your calculator, it's better just to use the table. Okay? We will see that later. Anyway, to kind of reiterate what we just said about the equivalence between a present and a future amount, or any given amount and an amount placed in the future with respect to it. Well, we define once again the equivalence, and is represented in such a way. So this is a simple cash flow with only one transaction at period K, which can be unspecified, can be 0 or anything, okay? And the equivalent future amount with respect to the P is defined with another cash flow placed n period after that, okay? I'm not saying anything new. I'm just representing in a graphical way what I showed you earlier in the table, okay? So I mentioned I will introduce some notation. The factor that we introduced last time, this one, okay, just to remind you, I'll just talk about it, is this formula right here, okay, has a name and has a symbol, okay? It's called compound factor. Let me say in advance, I won't really test you on these nicknames. I won't ask you what is a compound, as long as you know which formula to use, okay? That's enough. Anyway, since it has a name, let's call it as with his name, and its name, and is compound factor, which is instead something that I will want you to be able to recognize is this notation right here. So this factor here, which in this case is a very simple equation, is also represented with this notation, this one right here, okay? And this is read as, I want to calculate f, given this slash here stands for given these three parameters, p, I, and n, okay? That's how you read this. So you read this as f given p, I, n, okay? Which in this transformation, it's really nothing else than this mathematical simple equation, right? If you go in the opposite direction, if you want instead, as I mentioned before, if you want to instead calculate an amount which is in the past with respect to what you have, okay, which we will call f, the mathematical formula is here, again, nothing different than what I mentioned earlier, this one, okay, which also has a name, discount factor, and also a notation, which is kind of an inverse of that one. So will be, I want to calculate P given a future amount, interest rate, and number of periods in between, okay? So bottom line, if you look at the third row right here, we are repeating what we just said, P equal to a future amount multiplied by the factor, which can also be indicated as the future amount multiplied by the notation associated with that factor, okay? And similarly done for the first case before. So F, an unknown future amount, is calculated with knowing the present amount in the past with respect to F, multiplied by the mathematical equation, which is also indicated with this notation. So be familiar with this kind of notation because we're going to keep using it, and I will assume that you are familiar with it, okay? One other thing I want to mention, which is the bottom of this slide, I will try to avoid confusions here, okay? The equivalences are can be represented graphically in two ways. Okay, either the one that I like the most, by the way, the first one you see on top, where you have two separate cash flows which indicate the two amounts that are equivalent to each other. Okay, and in this case, as you notice, the arrows are both pointing up. Okay, the sign of the transaction is the same. However, as also the book does, you can represent the same equivalences with another background, okay? So if you look at this cash flow on the bottom right here, the same calculation, the same equivalence can be represented saying that if I invest a sum P, for example, in a bank, or you put some equity in a project, same kind of the same concept, and given my interest and given the period in between I want to do the calculation, I will be guaranteed an equivalent withdrawal from that investment, which is equal to this F amount in the future, okay? Which is calculated exactly in the same way as before, nothing different. It's just represented both in the same cash flow. So I don't want that to create confusion, but is I also thought about an analogy in algebra, which really, to me, is right on, okay? You all recognize that saying that A is equal to B is exactly the same thing that say A minus B is equal to 0, okay? I'm assuming all of you understand it, okay? So in a mathematical, in a money kind of mathematics, it's exactly the same representation. Either two different cash flow with an equal sign in the middle, or the same cash flow with different signs, okay? That's really just what it is. Okay, keep these things in mind, because I know statistically that there will be some confusion with some of you if you don't understand these basics, okay? Now, any question before I show you an example? All right, so the first example here, very simple. It's simply applying what we just discussed, okay? It's taken from your book, and we'll solve it together. So here it is, compute I add here an unknown present amount called P that would be equivalent to these two amounts shown in the cash flow right here, okay? So what this means, if you want to translate this graphical representation into practice, is you can see better thinking. Well, I will need. Think about yourself investing your own savings. Okay, I will need $2,000 after. Let's assume that the periods are years. Okay, for convenience, I will need $2,000 after 3 years from now because I need to do such and such. And I will also need $1,000 8 years from now, okay? So the question is, even that my bank is guaranteeing me a 5% interest during this time, how much I need to deposit right now to be sure I have just enough for these two transactions, okay? So bottom line, you want to know how much you need to deposit so that this P amount is equivalent to the sum of these two future amounts right here. Okay, so we have, and to reiterate what I said before, you can represent it in this way, okay, mimicking an investment of your money, or you can also represent it in this way, okay, where this amount P is equivalent to this future amount in the future in two separate cash. Okay, I'm pausing here and I'm repeating this concept because I want to make sure you are with me with that, because I really want to avoid confusion rather than create it, right? So, but it's the same thing represented in two different. So how do you go about solving it? It should be pretty straightforward. We'll do it together for the first time, okay? So actually, before I go there, let me show you the back of the book table. So if you go on your book or whatever version you have of the book, they should all have. I randomly open a page in the back of your book. As you can see, there are plenty of tables, okay, that you can use for the purpose that we are doing right now. So I'm opening randomly the page at 2%. The top value you see on the left top corner is the interest in which you do all the calculations. And then this and the first column are the periods in between the transaction you are considering. As of now, we only look at the first two columns, okay? F given P and P given F transformation. Later, we'll look at the others. Okay? But for now, just focus on the first two. And these numbers that you see here are simply the result of plugging in the correct interest and the correct N into the formulas that I showed you earlier, okay? Either this one or this one, okay? You can try yourself whether you're going from F to P or from P to F. You pick the right column and, of course, the right value to the calculation. Of course, you can do it with your calculator as well, okay? And it will probably make sense for this easy one. When you get to the left, to the right part of the columns here, you probably want to use the table because the formula are more complicated. Okay, we'll see. We'll get there later. Okay, so now let me show you how to use them for our purpose, for the example right here. So what we can say for this is that your unknown P is composed of two components. Okay, so you kind of divide it up in two parts, where the first component is going to be equivalent to the first future amount, and the second component will be the equivalent of the second future amount that you want to withdraw. Okay, and now you are left with simply calculating each one of these P1 and P2 using the formula that we discussed earlier. Okay, so for our purpose, we know that P1, again, P1 will be equivalent to your F3, and I'm referring to this F3 right here, and your P2 will be equivalent to your F, let's call it 8, as it is from the book. Okay, so you're just a matter of calculating it. The P1 will be, you see here, 2000 is your F3. Okay, and then as we saw before, I want to convert it to an equivalent amount, which is going to be obtained by multiplying F3 by the factor which is P. I want P given the future amount at 5% interest with 3 periods in between. Okay, 5% is given, 3 periods are easily seen by the cash flow. Okay, so I'm doing that, and I have a scan of the actual back of the book right here. So you go into the 5% page. Okay, you look at the P given F column because we are calculating that, and then you look at the 3 and you identify the correct factor for it. Okay, this factor is really nothing else than 1 plus 5% to the power of minus 3. Okay, you can easily verify that. So once we have this factor, we do a very similar thing for the second factor. This will be the second component, sorry. This will be your F8, okay, which is 1000. Okay, multiplied by the P given F 5%, so the same column, but with 8 periods in between. Okay, where the number, of course, is different. And once you do the calculation, right here, we have it all laid out as anticipated. Okay, so you do the math, and you get your deposit, your minimum deposit to guarantee your two projected withdrawal, in the future will be $2,404. Okay, plus 0.52. Okay, so this is how you do your calculation for this kind of equivalences. Now, let's use the same example. Before I go there, any question over this? Yes, I cannot hear you. I cannot hear you. Sorry, I cannot hear you. Yes, this is what we calculated for. So you have calculated that 2,400 more or less is what you need to deposit right now. Let me show you the cash flow. I need to deposit this amount, 2,400 right now, as a minimum, okay? As a minimum, because if you deposit more, you're just gonna have some saving left over, okay? But as a minimum, you want to deposit that to be able to withdraw this 2,000 after 3 years and also withdraw 1,000 after 8 years. Okay, and if you deposit the right exact amount, you're gonna be left with 0 at the end. Okay, you use all your savings. Okay, so rather than having 3,000, you only need to deposit 2,400. It makes sense because you are earning interest on your deposit. Okay. Anyway, so any other question? Okay, I use the same example to do the reverse thing, to kind of do the counter proof. Okay, somebody can say, well, I don't believe it. I don't believe that I think I need more or less, whatever. Okay, well, let's do the counter proof. Let's work from period 0 and see what happens in the future. So let's assume that we are actually going to deposit this amount as suggested by the previous calculation at the beginning. What do we know? That this amount will grow after 3 periods, 0, 1, 2, 3 period, okay? Because we have interest every year is going to accrue compound interest over that, okay? So using the same logic that I show you here, okay, the P amount after 3 period, it will become P multiplied by the factor, which is 1 plus I to the power of 3, okay? So, which in short is this one. So the book here is a little bit unclear because this F3 is actually not the F3 that is withdrawn. It's just, let's call it P3, okay? The present amount converted in the future after three years of interest, okay? It's, in this case, the book is confusing, okay? Because it's not the withdrawal, is how much I will actually have in the bank before the withdrawal, okay? So, and you calculate it as such, okay? 2404, your deposit multiplied by the factor. So the factor is represented also with the notation F given P 5% 3, okay, which I go back to here. The future amount given a present amount, 5%, 3 period, 1.157, and so forth, okay? Or you just plug it in your calculator, and you have it right here, and this is how much money, pretty much, you're gonna have in your bank after 3 years, if you leave it there for 3 years, okay? I'm sure this is pretty straightforward, okay? You just leave the money in the bank for 3 years. Then, what we know is that I need to withdraw 2,000 from that amount because I need to buy this and that, okay? So this one minus 2,000, oh, it's here, okay? This is actually your F3 as opposed to this one. So that's where the book is confusing, okay? 2,000 is withdrawn and you are left with the leftover, which is 783, okay? So at this point, we have only $783 in the bank. What else do we know? We know that we need to withdraw $1,000 after 5 years from that point, which is from the 3rd to the 5th. So in order to verify that, your F8, which in this case is appropriate to leave it F8, will be your current amount in the bank multiplied by the factor, okay, F given P 5%, 5. One confusion that I am anticipating is that why don't you use 8? Well, because I need to use the number of periods in between the two transactions I'm considering. So right now I am at 3. I need to see with this amount in 3 will become at 8. So it's 5 periods, okay? That's why we use 5. You do the math. You can also use the factor here rather than calculating with your calculator, and magically you're going to see that it comes down exactly to 1,000, okay? Which is exactly what you need according to the data of the problem, okay? So, and then we're going to have left with 0 after that. Okay, so this is actually a pretty simple example, okay, but hopefully helps you clarify whatever doubt you have. You have to get into the mind of this calculation. It's kind of off your typical civil engineering stuff, okay? So, all right, so that was the first example. Any question? No? Okay, before I go on with the other equivalences that we need to cover, which are a little bit more cumbersome and complicated, and they are here on the right part of the tables. We get there in a minute. I want to first talk to you about the so-called rule of 72, which is associated with the equivalence that we just discussed. Okay, so it's a pretty handy rule of thumb, okay, which once again refer to the P given F or F given P equivalence transformation. And what does it say? It says that a given sum, let's call it P or whatever symbol you want to use, approximately doubles in value whenever the product between the number of periods that you leave it invested on and the interest rate that is invested on during those periods, if whenever this product is close to or even equal to 72, okay, then your P will be becoming F equal to 2P. So it will double. Okay, that happens whenever this product is verified right here. One thing you need to be careful is that the interest should be entered in this calculation as, for example, if I say 5%, you put 5, you don't put 0.05. Okay, so that's just something to be careful about. Let me give you an example. Okay, so first of all, recall that a future amount given a P amount, once again, is calculated using the compound factor rate. Okay, we did that before. In order to verify that this is going to be 2P, okay, we only need to verify that this factor is more or less equal to 2. Okay, and in fact, if you look at the combination here, interest equal to 1, number of period in between the two transactions, 72. So if you have this combination, obviously the product will be equal to 70, right? If that happens, and if you plug in this value into your factor, you're gonna get the factor equal to 2.05, which is approximately double, approximately equal to. The same happens if you have the combination interest rate 2%, number of period 36, or 3, 24, 4, whatever combination makes it 72. You will see that the resulting factor is always going to be close enough, if not even exactly equal to 2, which will double your initial amount. Why this is important? Well, it's important because when you do, the context is when you do mental calculation, you want to see, instead of being in front of the computer, you are using this rule to figure out approximately number. When you're doing negotiation, when you're doing some rough estimation, something like that, okay? Nevertheless, this is another kind of concept which is required and routinely asked in the FEP exam as well, okay? So it's something that you should know. To give you a practical example, right here, well, I also have the answer here, but whatever. So imagine if the house market keeps growing approximately at 3% per year, okay? That's an assumption. Okay, so your interest in that particular transaction is about 3% per year. How long would it take for your own house to double its original value? Okay, you can use the rule of 72 to make that calculation. Okay, because as we just did, if your I is 3%, the I multiplied by N must be equal to 72. Okay, so this is pretty easy to figure out that N equal to 72 divided by 3, which is 24. Okay, so 24 years are needed for this example, your purchase value of the house to double in value. Okay, then of course you need to take care, you need to consider the inflation, which is going to reduce the value of the house as well. But just in numerical terms, this is what happened. Okay. Okay, so remember this, and pretty much you need to remember this very simple formula. And the only thing you need to be careful about is the interest rate needs to be entered as the percentage value. So it's not 0.03, it's 3, okay, in order to make it. Okay, still have, what is 1:30 at the end, right? Yeah, 12:40, 1:30, right? So I still have 15 minutes. So now we are eventually going into the second two columns right here of the equivalences, which are associated with the so-called uniform series calculation. Things get a little bit more complicated, okay, in the mathematics, but concept-wise, we are pretty much talking about the same thing. So I don't want you to get scared about the mathematics here, because I won't actually test you on the mathematics here, but I want to, show you what is referring to, okay? So what we are doing here is, similarly than before, we are trying to identify formulas which can help us figure out equivalencies between a single amount, let's call it always P, at whatever period, generically K, okay? Equivalence between this and another cash flow, which must have this kind of shape, okay? Must have this uniform series of transactions, all equal to each other, which are starting, this is important, starting one period after the period in which P is, and they keep going for n periods start. So you have n arrows starting the period right after where P is, okay? Of course, K can be anything, N can be anything, and the amount can be, of course, changed, okay? However, what we are interested in, and this is important in particular for mortgage, okay? Mortgage calculation, I'll show you an example later if I have time, probably I do. You can follow the mathematics here pretty much for your information. I'm not going to test you on that, but if you want, you have, if you treat the arrow as a single future amount, okay, you can do the conversion by doing a P given F for each one of them, okay? So I am treating them as a single future amount and moving, in quotation, moving them back to the present, okay? And if I do that, and then I do some mathematical manipulation here, I multiply everything by 1 plus I, and then I do this equation minus the first equation, I am reduced to this much shorter equation, okay? Again, for the math enthusiasts, this is good to read, but I won't test you on that, okay? So once you get to this point, you can rearrange and solve for either A or P to go from A to P or from P to A, okay? Whatever you want to calculate it from. As I mentioned before, this will be a little bit more cumbersome to put in your calculator to do the calculation whenever you need to do that. So we have a similar notation as we did for the P given F. Here, in this case, we have the factors are, I want to calculate A. Of course, A is referred to this, okay? Given a present amount P, interest rate I, and a number of period N. The second formula instead, I want to calculate P, given a uniform series A, interest I, and number of period N. Again, these factors have names, capital recovery factor, which is similar to the one before, and present worth factor. Present worth factor is something that we are going to encounter a lot from the second week on. Something that I didn't mention yet in this slide, but it's similar than before, is that the equivalence, once again, can be represented as two different cash flow equivalent to each other, or represented in the same cash flow with different signs. Okay, so that this makes more sense in practice. I invest an amount P, which is equivalent to all the uniform series that is in the future. This is actually a direct representation of a mortgage, of a loan. Okay, think about, you look at this cash flow right here and think about it from the bank perspective. What the bank does to you. If you go to the bank and you ask money for a student loan, okay? Well, the bank gives you the money that you need to pay for your tuition and is expecting, usually, I don't know how the student loans work, but certainly the house loan works this way, expecting you to pay monthly an equivalent amount, a fixed amount up to the end. The combination of this amount A will be equivalent to the original loan that they give you, okay? Of course, given the interest and given how many periods you have to pay, okay? So this is nice in practice because you can, quotation, simply calculate either one of those two, even the other one, by using these formulas right here. Okay. Before I go to the example, time permitting, and I hope I can make it, there are a couple of special cases when the number of periods associated with this equivalence goes to infinity. Okay, you may say, doesn't make any sense. Nobody's going to pay forever. Nobody's going to get the money forever, right? However, it does make sense when you're doing planning for very large projects, especially in civil engineering, because sometimes you are building such a massive structures that you don't really see an end in sight. Okay, so for example, you build a dam, you build a highway, you build a building, you don't really foresee that it's going to be dismantled, right? So the life is considered forever, right? With this in mind, it does make sense to use this modeling, okay, for the financials associated with those projects, okay? So things get easier because if you substitute n equal to infinity in these two math equations, eventually the two factor will become simply I and 1 over I. Okay, as you can easily check yourself. Okay, so we will use them because also in the examples, because again, they are really handy when you are doing project evaluations. Okay, big project evaluation. Before I get to the mortgage example for my last 8 minutes, more or less, any question? Yes. Yes, good point, actually, I should have mentioned. This A, and I'm writing right here, is every arrow is an A. Okay, every single arrow is equal to the amount, whatever A is going to be. To make it more practical, it's like your installments if you pay off the mortgage, okay? Whatever you pay every month, which usually is the same amount, okay? It's not always the case, by the way. You have more complicated repayment structure, but the most common, particularly in the US, I would say, is this flat amount, okay? Any other question? Speaking of which, I will go over this last example, which is, as promised, the mortgage, okay? Which directly applies the uniform equivalency that we just did, okay? So let's assume that I'm reversing the cash flow right here because it's from the customer perspective, okay? Customer is buying a house. Any of you, sooner or later, if you didn't have it already, okay? You will buy a house, hopefully. So let's assume that you need $100,000 to do that, okay? To pay the balance in addition to your initial deposit. And you are negotiating with the bank a 20-year mortgage loan with monthly payments and a monthly interest rate of 2% per month. This is a little bit off what are the current rates, but a few years ago it was around that value, okay? A little bit higher. For the purpose of the mathematics, for the example, it doesn't matter, okay? It can be anything, and number we just change. So let's first translate what this means. It means that the payments are supposed to be monthly. So the period associated with this cash flow is a month, okay? It's not 20 years, it's not a year, don't get confused. It's year in total, but the cash flow is divided in months, okay? So number of period will be 12 months per year multiplied by the 20 year. So you are repaying your initial loan in 240 periods, 240 months. And the contract says that you are going to pay 2% interest for every single period. Okay, of course, on the outstanding balance. Remember that, because it's not on the initial value. So how do you represent it? As such, this is your cash flow. You get a positive transaction at the beginning because the banks gives you $100,000. However, this must be equivalent to the repayment structure down here, which goes from one period after your initial loan transaction for 240 months, okay? And you are expected to pay every month a certain amount. Question is, for this example, what is that amount? Okay, how much you have to pay every month to make sure that you are abiding to the contract with those specifications right here. Well, guess what? You can use exactly the equivalency that we used before, that we discussed before. So your monthly payment will be calculated, switch back to this, using this formula right here. A will be your loan amount multiplied by the factor. So P multiplied by A given P IN. Okay, you do the math, which means you can either plug in the value in the formula in the expression before, or more easily, you use the back of the book table. It's a little bit too small here, this one maybe, but if you look closely, there's the 2% page, which is associated with the 2% you have here. You're looking at the A given P column because you want to find A given a certain P. And you look at the 240, sorry, here it is, 240 periods of your mortgage. And this is the factor that you need to use, which if you cannot read it, it's 0.020174. So if you multiply this by 100, which is your initial amount, so that's normal zoom here, you get that your monthly payment to make sure that you abide to the contract is a little bit over $2,000 per month. And I don't know whether you ever dealt with this kind of mortgage before, with you or your parents, I don't know, but you can easily double check the amount that you pay with this formula. It matches. Okay, of course, on top, you're gonna have some transaction fee, some kind of other BS, right? But the actual money that you have to pay for the loan itself is calculated exactly with this. Okay. All right. Any other question? Okay, so I will actually post homework for next week, okay, even though it's the first 2 lectures only, and I will post it on Canvas, and I will expect you to submit it via Canvas, okay, by next Friday. I will be more specific on the actual homework, and I will see you on Monday, okay? No, not yet. Have a good weekend.